Wang from Guangdong Technion, Israel Institute of Technology. Tonight, I'm very honored to be your host. I would like to extend a warm welcome to all of our attendees joining us online. So we have an exciting evening planned featuring talks from three distinguished researchers in wearable technology, bioelectronics, and flexible electronics. So joining me as a panelist for the Q&A session later is Professor Shiming Zhang from Tsinghua University. So let's begin our first speaker, Professor Shiming Zhang from University of Hong Kong. So Professor Zhang's work focuses on the development of tissue like microelectronics that link the humans and the machines, revolutionize the field of wearable bioelectronics. So before Shiming's talk, so let me introduce him first. So Professor Shiming Zhang is currently a professor at the University of Hong Kong, leading a wearable research group. So he has a transdisciplinary training record across the field of microelectronics in his bachelor's degree, electrochemistry during his PhD degree, and biomedical engineering during his postdoc training, so making him uniquely qualified for wearable bioelectronic research. He currently holds a cross-departmental appointments at the University of Hong Kong Engineering, HKU Medical School, HKU Shenzhen Hospital, and the Terasaki Institute affiliated at the University of California, Los Angeles, UCLA. So this resourceful and complementary and collaborative research environments with Professor Zhang as the coordinator has led to the development of the first wearable biosensing platform at HKU, so the perfect wearable platform. So without further ado, Shiming, please, the floor is yours.
Yeah, thank you very much, Professor Wang, for the kind introduction. And also thank Professor Zhang Haiqia for the organization and also Professor Qu Xiaoming for the kind invitation. So let me share my screen now. Let me check if it works or not. So, can you see the full screen now?
Yes.
Okay, thank you very much. Yeah. So thank you very much again for the kind introduction about our work. So the title of my talk today is tissue-like microelectronics linking humans and machines. So basically, I will introduce you a new kind of microelectronics technology, which is kind of try to acquire tissue-like properties, such as stretchable and self-healable properties, and to deploy between the interface between humans and machines, basically human-machine interface, right? And how we can develop these technologies for practical applications. So yes, for me, so as Professor Wang has already kindly mentioned, so I'm now an assistant professor at the Department of Electrical and Electronic Engineering at the University of Hong Kong. Also, I'm affiliated to the State K Lab on pharmaceutical biotechnology at the Hong Kong Medical School. Also, I'm affiliated to Terasaki Institute for Biomedical Innovation at the LA. So currently, as a teacher, so I'm teaching multiple courses at Hong Kong U. So the first one is circuits, electronic circuits, and wearable bioelectronics, and also electrochemistry and the soft materials. As you can see from my really interdisciplinary teaching, so you know that we are doing really interdisciplinary research in this direction. So this is the outline of my talk today. So let's just go straight into the core, which is the organic electrochemical transistors. So I think maybe some of you know this, some of you don't know. But if you don't know, just in short, is a kind of microelectronic transistor technology, and this kind of transistors are very good candidates to be used for in vivo or implantable or wearable bioelectronics applications because they can be really soft and, for example, other tissue-like properties, as I mentioned. And the second is tissue-like OECTs, that how we can develop tissue-like OECTs, because normally OECT actually are fabricated on glass or plastics, but in order to make them stretchable or healable, we need to develop them on elastomers or even hydrogels. And the third part is hydrogel OECTs. This is actually in the late phase, and we try to bridge hydrogel with OECT to see if we can just further gain some tissue-like properties for this kind of microelectronic devices. And the last one is Hong Kong Perfect wearable system, because we want to have a fully integrated system. So we need to really have a wearable platform. This is mostly electrical circuits design, and I will introduce later in this topic also. So first of all, I just want to borrow a slides from a very reputed professor in electrochemistry in China. So there are only good research come from solving good questions. So actually, we are solving question, which is actually let's say the wearable electronics or wearable bioelectronics. But this question does need solutions from these different disciplines. We need the convergent engineering efforts and collaborative research efforts. So with time pass by, so this kind of disciplines will come together. But finally, they will just merge together to solve this question. And this is the time when a new discipline can form. I think you may agree with me about this approach. These are just take the slides here. So this is a comment paper we comment. It's actually a paper published by Professor Takosamaya Group at the University of Tokyo. But we dropped this comment on this one just to let you know that this technology, OECT, organic electrochemical transistor, can be a really very ideal transducer to be deployed on the skin device interface. And this device can be mechanically soft and really skin conformable, and to convert the biological signals to electronic signals. And it's a very efficient one compared to the current available technologies. And you can see also it's kind of active or a new kind of electrodes technology to be used to replace the current electrodes to get high quality data. You may heard of AI or very advanced signal processing method, but I think the first step is to get high quality data. High quality data are obtained from high quality sensors, and OECT is a high quality sensors that can be used at the skin device interface to get this kind of information. So again, as I mentioned, we need to move from rigid ones to tissue-like ones. So we need to change everything. The bottom is from materials. So traditional one, for example, glass, silicon, this kind of rigid materials, we cannot use them anymore. We need to explore new materials. For example, stretchable, heatable conducting polymers, hydrogels, elastomers, conductors. So we have to find the best one that is suitable for OECT use, right? And then that's actually new fabrications, because they are soft, tissue-like, devices. They may not be compatible, for example, with traditional microfabrication photolithography technologies. For example, the solvent may just swell them, vacuum can just destroy the properties of the soft material. And by making this device, you may observe some new phenomenon. For example, electrochemistry in porous and soft materials, let's say conducting polymers or hydrogels, they may be different, right? So you need to study really the electrochemistry behind. And by doing so, you may observe some new functions. For example, you can have the self-healing ability, or you can maybe observe some really low performance or either high performance, or either strain-induced enhanced performance or weakened performance. So these kind of things that we need to explore these kind of new functions in detail. But to study this, actually, OECT itself, as mentioned by the name, is also very interdisciplinary. For example, it is involve organic electronics, which actually the first term is organic, and the electrochemical. So you need to study electrochemistry. And the transistor, of course, is a kind of microelectronics, right? Which is also in the title of my talk. It's so transdisciplinary and need to solve so many things together, right? But if you can solve this tissue like OECTs, it can be a new device paradigm. For example, as I mentioned in the last slides, and it can be used for emerging BME applications, bioelectronics, and wearables as an advanced transducer. Hope this can convince you. Okay. But what is OECTs, right? I have blah talk a lot of things, but what is OECT? I think many of you may be familiar with the transistor, right? But OECT is also a transistor. But the different thing is that it operates at a very low voltage, for example, less than 1 watt, or even actually less than a few millivolts. It still can have the transistor performance. How it works is that when you have the very small potential applied on the gate, can be millivolt scale, so it can push the ions into a conducting polymer. Let's say in this case, the conducting polymer P.PSS. So the ions will have actually a reaction with the conducting polymer, redox reaction, which is reversible, and then it can change the conductivity state of the P dot. For example, ions moves in can reduce the conductivity, and ions moves out can just restore the conductivity, which is highly reversible. So in this case, actually, by nature, it converts the ionic signals to electronic signals. Okay, so this is the reason why OECT is the perfect link, okay, between humans and machines. Humans conduct ions and machines conduct electrons. I hope you can understand or agree with this kind of sentence. Okay, so in this case, actually, we have ions from the tissue, electrons from the electronics, and OECT is a very good bridge or the linker, right? But normally, for example, we use the passive electrodes, so ions only convert to electrons equivalently. For example, you have a capacitor, you have 1 ions, you just absorb 1 electrons. But how we can just amplify this? We don't want to use simple mathematics. We want to use advanced mathematics. For example, we multiply a factor, then we can actually improve the signal to noise ratio, right? We can increase the signal intensity. But transistor is just doing this job, right? So as long as we have a transistor, so because the input impedance is very high and output impedance is very low, actually it can amplify the ions numbers by a lot of numbers of electrons. This actually is called the gain or amplification ratio. Okay, this is transistor called transconductance. So OECT so far has the highest transconductance because compared to CMOS transistor, which only have the surface modulation, OECT actually the ions can penetrate into the bulk. So it's called volumetric capacitance, which leads to higher capacitance ratios. And this combined with other properties, for example, OECT is also organic, make it biocompatible, conformable to be used for implantable and wearable applications. And also there's some others, for example, here it's transparency, which means that they don't have the optical artifacts with, for example, optical technologies, MRI, CT, etc. So this actually makes it very useful. But how you can experimentally verify this? Actually, this work is done almost 10 years ago, 11 years ago, pioneered by Professor George Maller's group, so who is actually currently at the University of Cambridge. So suppose you have the signal here, and then normally you need to amplify this signal, offline from them, or just far from the source of the signal. For example, a source of the data. For example, here you have the differential amplifier. If you amplify here, you also amplify the noise on the line. So actually, you amplify everything. Your signal to noise ratio, which is the golden standard to evaluate a transducer, does not really increase. But if you can deploy the amplifier closer to the source of data, for example, here, actually, you will avoid amplify the noise on the line. Finally, you get higher signal to noise ratio. Okay, so Professor George Maller's group has already verified this around 10 years ago that it does improve the signal to noise ratio, SNR. Okay, actually, in 2018, Professor Taku's group also verified this can improve the SNR of the ECG in the animal study. Okay. So OECT is special because OECT can be deployed closer to the source of data. For example, brain, as I mentioned, it's organic devices, right? It can be soft and conformable. The other one is also allowed in sensor edge computing, which is a very hot topic now, because if you have some edge computing components, that means sensing and computing can merge together here. It can make some local decisions, which is really very advanced because OECT electrochemical part actually can do the sensing job, but by nature it's a transistor, it can do the computing part. So actually is really very popular here. But what we are doing is that we focus on the wearable applications. So I think we need to solve two key problems. The first part is that device level, as I mentioned, we want to make the OECT tissue-like softer, right? So it reduces the motion artifacts and also the long-term, implantation time, because it can potentially reduce the this kind of foreign body reaction. And the second one is system level. We want to make the system much smaller so that we really can have a fully integrated system that can be deployed. Because normally we need to have cables, right, connect to the lab machines, which is actually not very convenient, right? So this is a paper which we published 2 years ago, invited by Professor Natali at Georgia Tech. So she kindly invited us to draft a highlight on our tissue-like OECT. So basically, we just give a historical trace back to our first demonstration of the OECT, stretchable OECT, and then many details here. If you're interested, you can go to see this paper. Just to introduce you here. So actually, in 2017, is around already 7 years ago, we published this paper, the first stretchable organic electrochemical transistor. So at that time, we did nothing new, I think, but what we are doing is transdisciplinary. So I think we conceptualized the way we can use a stretchable hydrogel. At that time, actually, Professor Gong Jianping and Su Zhigang, they did a lot of things there. We just bring this concept here. And we pre-stretched something that actually is pioneered by Professor George Whiteside and Professor John Rogers, right? So we pre-stretch the device, we use a hydrogel, and then we optimize the interface so the hydrogel can attach very well to the substrate, and we can make a stretchable OECT transistor. So the device can be either big or small. So for example, I show a big one here. So on top is hydrogel, on the bottom, at the bottom is a non-polymer. So it's really very highly viscoelastic. Okay, it's highly viscoelastic. And also it cannot be transparent. It's actually also colorimetric if you're familiar with PSS, right? For example, I show here a fully stretchable device. So all the substrate, the electrolyte, and the insulating layers are made of, kind of rubber-like or gel-like materials. Okay, it's kind of very stretchy. Okay. But again, so as a microelectronic device, we want to make it smaller, right? So we use some new pattern technologies. For example, here is actually we use paradigm. You may be familiar with paradigm, but we make paradigm very thin, 2 micrometers, and we open holes on top. Then we peel off paradigm from plastic to use paradigm as a photolithography layer, peeling off it. And then we pattern the gold on PDMS. As you can see from this actually GIF, the gold patterns on PDMS is very kind of high yield. So normally if you pattern gold on PDMS, if you're familiar with photolithography on soft materials, the device yield actually is very low, but we make it actually relatively good. The device performance is also good, and actually this is the first stretchable OECT, and this actually is recognized by peers in this field. For example, this is a paper recently published. So after studying a lot of time on these stretchable OECTs, and then I realized that we still need to combine OECTs with better materials that have better tissue-like properties. So, and then I joined Professor Ali Kadam Hosseini group. So Ali, as you may know, is a world-leading expert on hydrogels, and also published a lot of actually amazing works on hydrogels. But then I have the idea how we can leverage the tissue-like properties of hydrogels for microelectronics, right? So apparently there's a lot of things to do. And then I joined Ali's lab, and then get a lot of suggestions from Ali and also the team members there. It's also a very interdisciplinary lab. I learned a lot. But then in short, so in 2020, 2 years after I joined the lab, so we developed the hydrogel OECTs. Basically, this channel is not the thin film anymore. For example, traditionally we make organic electronics, we make it use of thin film. But in this case, actually we have a thick hydrogel. We just do some hydrogel engineering and to enable these hydrogels not only stretchable and porous, but also have this kind of semi-conducting property or redox active properties at that time. We focus on processing, not molecular level. Okay, and the transistor works very well. Also, we can process this hydrogels for example, like injectable hydrogel fibers or even implantable hydrogel fibers. So you can play them in different formats. Okay, so this is really kind of fantastic, and the transistor operates very good in terms of output and transfer curves. Okay, I think this is the first time that we develop hydrogels that can be used as a semiconductor channel for transistor applications, and also it can gain the tissue-like properties. Okay, so this is also recognized by peers. For example, Professor Takata at the University of Tokyo mentioned that actually we report the first hydrogel used for OECD channel, which OECD the transistor, right? But along this way, actually, we also observe something other tissue-like properties because we focus on OECT, right? What we found is that actually, if you the thickness of the hydrogel or the film, it's hard to define, right? But because actually, thin film by nature is also hydrogel. So if the thickness is about 1 micrometer, just 1 micrometer, is not thick, right? It still maintain a semiconducting film. Then as long as the water droplet touch the gap, it can heal automatically. Or even though it's not a water droplet, but it's humidity. For example, we change the ambient humidity from 60 to 90, then it can heal the current. This is the initial current, we cut it, and then we just change the humidity level, then the humidity level reaches 90% the current responses, right? And then after the panel heals, it still can be used as the channel material for OECT. That means this OECT actually is self-heatable, right? So it does gain tissue-like properties in the framework of a transistor. So we report this paper actually in 2017, and after that, so actually you can see almost every year. So that's actually materials advances in this field. Okay, some of them are from our group, some of them are not. So it's just this domain. So this actually is also recognized by peers. For example, we observed the first water-induced healing of the P-PSS films. So what I think we want to mention is that P-PSS is a very popular material, is used by the whole public, worldwide, right? But actually, we just get a chance to see. I was check actually Wikipedia, and then actually the P-PSS can also show self-healing properties if submerged in water. So this actually is written into the Wikipedia, and then we noted that actually the following reference is just our work. So this actually makes us feel encouraging to further research in this field. But fundamentally, we observe something new and to develop materials and then for OECT. But then how to realize scalable scalable manufacturing of these tissue-like transistors. So actually, after I started my own lab, almost 4 years ago at Hong Kong U, so I formed a transdisciplinary research group. For example, my first year PhD student, Bai Jing. So he is really very good at printing technologies. So he developed this printing platform by himself. Okay, this is multi-channel printing. So you can print conducting polymers, hydrogels, and the insulators, and also even the conductors, for example, gold and silver inks. So as you can see, the reliability is very good, and also it can scalable. The minimal resolution is down to 100 micrometers, as you can see from here. And the device is actually very reliable, it's stretchable. You can scale up them from single device to really kind of thousands of the devices together. And so this is actually my another PhD, Jia Liu. So it's also my first year PhD, who's really very good at materials and this kind of multi procedure fabrications. For example, this device, this OECT circuit, so that's actually printed gold on the elastomer. Printing gold is very challenging, right? Because actually we are challenged by by the peers, also encouraged by them that you cannot use silver because silver is not electrochemically stable. So we need to use the gold. And then we found many ways to finally we managed to print the gold on the elastomer. And we have the conducting hydrogels, semiconducting hydrogels, insulators, all in one shot. We print all these kind of materials together to form this kind of stretchable transistors arrays. As you can see, that we can make a scalable fabrication of the tissue-like stretchable OECTs, on this kind of stretchable substrates. Okay. So this is the last part I want to introduce. As I mentioned, that we have some material solutions, device solutions for tissue-like OECT, but to further leverage the potential of this kind of new device technology, we need to have a readout system, and this is actually mostly done by PhD Tian Xinyu, whose background is electrical engineering and also very good at the circuit design. So in the first year he came to the group, actually he designed this perfect system for OECT measurements. It's customized for OECT measurements. There's a lot of actually customized design at the behind. For example, actually we go through, I think maybe more than 20, 30 versions of iteration of this kind of readout system. And we candidly, sitting together, name it personalized electronic reader for electrochemical transistor perfect. Okay, this is the reason why perfect is called perfect, because it's personalized for OECT application or ECT transistor characterizations. So actually there's so many variants, but finally we make them very small, and also we have the relevant readout APP at the computer or cell phone. So this is a recent publication. So to use OECT for biosensing application, and the most popular one, of course, as you know, is the continuous glucose monitoring, right? And we just use OECT, this kind of platform for OECT for the CGM application. Of course, in the same time, we also leverage the use of microneedles, because the microneedle is kind of emerging sampling technology to enable the minimally invasive biosensing functions. And this actually is collaborated with Professor Shiming at the Hong Kong U Medical School, and also Professor Gu Zhen and Wang Jinqiang at Zhejiang University, so on this topic. So I just want to show you, on the device level or transducer level, from the circuits part, how OECT can really contribute to some new values to the current CGM. Because you may say that current CGM is already enough for use, right? So the blue part actually is indicated for OECT. As you can see, OECT is a transducer, right? So it can actually change the amplification ratio of the CGM of the any kind of relevant sensors. So in short, it can just modulate the SNR or resolution. For example, here in this figure B, so you have the detection range here can be very large at the beginning if the sensitivity is low, this black curve. But with OECT, you can simply change the gate voltage and you can change the GM to be high. In this case, you may have a decrease in the detection range, for example, this X, but you got a boost in the ADC count, which is the resolution. That means with OECT, you can play a trade-off between the detection range and the resolution, right? And sometimes for precision diabetes care, you may want to zoom in into certain part to have higher resolution for some, for example, prediction or for some, feedback into insulin delivery, right? In this case, actually, it's very important. And also, OECT improves the SNR. Theoretically, actually, if you have the concentration goes down, for example, insulin is 10 to the power of the, -9. So in this case, actually, it can improve the SNR ratio. This is very important. We also experimentally verified actually that, this OECT or CGM have very high SNR compared to the conventional CGM sensor, and it may be more important for detecting ultra-low concentrations biomarkers in the future. And finally, I want to thank my team. For example, this is my team, partial, and also my mentors, collaborators. For example, my postdoc supervisor, Ali Hosseini, my PhD supervisor, Fabio, and also my collaborator, Professor George Malas, Professor Beyond Liu, Professor Shiming, Gu Zhen, and Yixing Ge, Yang Zhangui, and etc. And also the founding agency. Thank you very much. Yeah, thank you.
Thank you. Thank you, Professor Zhang, for your wonderful presentation. Very impressive research. I believe the online get a lot of knowledge and inspiration from your talk. So our last speaker Our last speaker is Professor Sungjun Park from Ajou University in South Korea. So Professor Park's research focuses on the development of ultra-flexible and skin-compatible organic optoelectronic devices. So before his talk, let me introduce him to us. So please note that you feel free to submit your questions using the chat function as many as possible during the discussion session. So Professor Sungjun Park is from the Department of Electrical and Computer Engineering and the Department of Intelligent Semiconductor Engineering at Ajou University, Republic of Korea. So he earned his PhD in 2016 from the School of Materials Science and Engineering at Gwangju Institute of Science and Technology, Republic of Korea. Before joining Ajou University in 2020, he conducted his postdoc research at RIKEN in Japan and worked as a senior researcher at Samsung Advanced Institute of Technology in the Republic of Korea. So Professor Park's research focuses on developing novel solution processed electronic devices and integrating them into flexible and stretchable electronics for wearable sensors. He published extensively in top international journals, including Nature Nanotechnology, Nature Energy, Materials Science and Engineering, reports, Advanced Materials, Advanced Functional Material, PNAS, etc. And he also serves as the lead guest editor for the MPG Flexible Electronics collection. Beyond his academic achievements, Professor Park holds 18 US patents and has successfully completed 3 technology transfers to industry, amounting to approximately 0.3 million USD since 2021. That's very amazing. So without further ado, we will welcome Sungjun Park to start his presentation. Sungjun, please.
Sanjo, you're mute. So you mute, please turn.
Hello, everyone. Can you hear me?
Yes.
Okay. So thank you for your kind invitation and thank you for good introductions. So my name is Sungjun Park and I am the associate professor in Ajou University located in Suwon. And I would like to give my gratitude to the all committee member and Yan Wang and Su Xiaoming and our staff Alice for the kind invitation. And today the title of my presentation is Ultra Flexible and Skin Compatible Organic Optoelectronic Devices. So since I joined the Department of the Electrical and Computer Engineering and Department of Intelligent Semiconductor Engineering at Ajou University in 2020, so our group, consisting of the 13 members, has been fully committed to exploring various and exciting topics related to the futuristic and functional electronic devices, sensors, and energy harvesting systems. And my school at university is located just 30 minutes from the central Seoul and an hour from the Incheon International Airport. So I'm always welcome to the people who is working on the soft electronics and other researchers. And it is not only known for its strong focus on research and innovation, but also we are trying to focus on excellent collaboration with foreign researchers. And our university offers the vibrant and the diverse academic environment, making it an ideal places for the students from around the world and to experience high quality education and sciences in Korea. And during my research period, the mechanical deformation of the electronic devices is always in my mind. So based on the organic and or inorganic functional electrical materials, I focused on the material characteristics and fabrication process and electrical properties and their application into the human-machine interfaces. So basically, I started on the molecular scale electronic devices, so using the single molecules as one of the electronic component of devices. And then I also worked on the solution process, the metal oxide electronic devices, to lowering their temperature to be compatible with skin compatible or flexible electronic substrate. And then I tried to more focus on their application and why they need to flexible and which area they can be applied, so that we now pursue more flexibility and or stretchability of the devices that can be durable even under very harsh environmental conditions. Sorry. So nowadays, our group especially focuses on the high performance and functional electronic devices on flexible and or stretchable substrate. And second one, we also trying to develop the ultra low voltage operated electronic devices, such as the organic electrochemical transistor, which is already presented by the Shiming. And also we are also trying to working on the using the active materials as a metal oxide electronic devices, which is electrolyte gated, the metal oxide electrolyte sensors. And by combining both those two designs, the skin and the tissue compatible electronic devices can be achieved. And we can also record some kind of the electrical data from the skin or human body surfaces. So actually, there are a lot of information we can get from the body and or tissue surfaces, including the brainwave and cardiac and muscle activity and temperature, sweat, and so on. So there are also a variety of information from the sweat. And to measure such kind of the biosignal data, the devices should be lightweight and non-invasive to human body. And the development of the skin conformer and optoelectronic devices is one of the good candidates for future and smart integrated system to monitor physiological condition continuously. Among various types of the electronic devices, organic-based electronic devices is one of the good candidates as a futuristic human-friendly sensors, because their Young's modulus of the organic materials are 100 times lower than a silicon or inorganic materials. And at the same thickness, we can achieve the soft electronic devices because their flexural rigidity is much lower than the other inorganic and or silicon materials. Also, by reducing their total thickness of the devices down to few micrometer scale, we can achieve highly soft devices that can be applied into the skin and or tissue compatible sensors because of similar mechanical properties between the skin and the devices. So as you can see, the skin shows the 10 to 6 Pascal of the mechanical softness, which is Young's modulus. But by designing their total thickness lower than micro scale, we can have a much more softer devices. So here is one of the good example published by Rogers Group in 2013, and they showed that some of the metal whose thickness of the 500 micrometer on top of the very complex surfaces, they shows the air gap between the metal and some kind of complex surfaces, but some metals, their thickness down to 5 micrometer scale, the excellent conformability can be achieved between the interface between the some metals and the complex surfaces. Using such kind of strategy on the devices, they could demonstrate the multifunctional sensors on forehead surfaces, and finally get the biological information, including such as the temperature, sweat information, and the electrocardiogram data. Here is the other strategies also suggested by the Professor Martin and the Professor Somea in 2013. And they developed the world thinnest and lightest TFTs on the ultra thin substrate layer. And the device array shows only the 3 grams per meter square. And they made a new era of the ultra flexible devices. This is the different approaches using the bottom-up processes on the ultra-flexible substrate. And after that, we could say that in 2003, some kind of sensors on the ultra-flexible substrate, they can be used as the prosthetic applications. But now, by demonstrating such kind of imperceptible design, we can say that the devices can be synchronized with the skin surfaces, and they even know what happened under the skins and also outside of skins. So today I'd like to a little bit more focus on the organic optoelectronic devices. So when the light is irradiated on the devices, the extons can be generated in the bulk heterojunction layers, and then electrons and holes they can be extracted to the bottom and top electrode. We can see the electrical data such as voltage or current data. And those devices can be applied into the flexible application, or by applying the semi-transparent design, they also applied into the building window applications and also indoor applications. And nowadays, the organic-based solar cell shows the high efficiency approaching 20%. And I would like to show you how those ultra-flexible organic optoelectronic devices can be historically developed. And in 2012, Professor Martin shows the world's first lightest organic solar cells published in the Nature Communications. And he demonstrated organic solar cells wrapped over the one hairs. And you can see in this slide, and they show the 4.2% of the efficiencies and the ultra lightweight around 4 grams per meter square. In 2017, the Dr. Jino shows the textile compatible organic solar cells, and by applying the double-side encapsulations, and they show the world's first washable organic photovoltaic devices via double-side encapsulation. So as you can see, the solar cells can be operated in the aqueous conditions, and double-side encapsulation shows the very the reliable device operation even in the aqueous conditions. And this one is achieved by the Professor Shiming Zhang, who is a panelist today, and she showed the highly efficient organic solar cell modules exceeding like 36 milliwatt in 4.4 square centimeters. And using the PVD TTT or FT, which is novel polymers, she shows the great module devices on ultra flexible substrate. And at the same time, I demonstrated a little bit different focus on the biomonitoring system using the organic optoelectronic devices. This is the first ultra flexible and near IR responsive to the organic photodiode. And then when the device is attached on the skin surfaces, as you can see, the along the wrinkle on the fingerprint, the devices were attached on the skin surfaces, and by attaching this very thin and good adhesiveness, we can get the high signal to noise ratio of the PPG signals. So here's one of the demonstration. So left side, this is commercial PPG sensors, and right side is just showing the data using the laptop, and using the ultra flexible organic optoelectronic devices, we can achieve the very good signal to noise ratio using of the PPG signals. Not all about me, I mean, all over the researchers in the worldwide, they trying to show the skin compatible sensors or skin compatible displays or energy or integrated system. But when we focus on the sensors on the skin compatible design, there are a bunch of the biological data can be recorded, but mostly the signals from body is very small, and it's hard to get hard to make the data very easily because of the dirty noise from the the built-in power sources. So normally the noise can be influenced by the ground loop or AC line noise or wire noise, or sometimes RF interferences can also affect on the gathering the biological data. So it should be removed by the dirty noise signals when we try to get the biological data. So at the time, my research motivation is to establish the ultra flexible and pure energy sources, and which can be directly integrated with the electrochemical transistor sensors to get the very high signal to noise ratio of the biological data. So the three strategies applied to achieve the highly efficient organic solar cells. So there are three strategies, which the first one is the materials. So I normally use the PVD TTT OFTs instead of the PTB7TH, which is very standard materials. But PVD OFT, they have a linear side chain, so we could achieve the much more crystallized organic materials, and also those linear side chain can show the durable organic layer properties under the harsh environmental conditions, and also by applying the zinc oxide nanoparticles instead of solution processed Jorgal zinc oxide layer, we could minimize the energy intensive process, for example, annealing temperature to form the high quality zinc oxide metal oxide layer. And the other one is that we also apply the 1D grating nanostructures on the electrical transporting layer and also active layer both. So by applying those three strategies, we could achieve the shiny surface of the organic solar cells and could achieve the shiny surface of the OPVs and highly efficient solar cells. And the delamination of the solar cells from the supporting glass is quite easy. So by applying the sticky tape at the edge of the glass supporting substrate, we can simply detach the cells from the glass substrate. And then after cutting off the other different tapes, we could achieve the 36 microgram per devices, which is very lightweight of the devices. And to comparable with the skin surfaces, we need to ensure the mechanical durability under the harsh conditions. So the device is laminated onto the pre-stretched elastomers, and we did some forces to the central side, and up to 33% of compressions was applied onto the devices. So by applying the pressures to the center side, we could measure that the devices were operated under the harsh mechanical deformation, and also by cycling test under the 900 repetitive cycles with the 33% of compressions, the devices can be well maintained above the 7% of the power efficiencies. So as I told you, the pure power sources and their integration with the sensor is quite important when we try to measure the biological signals from the skin surfaces. Because to minimize the noise sources, so as already the Shiming said, the organic electrochemical transistors is really good and very important device unit to measure the biomonitoring systems. But to operate those devices, the only one board and also the under the one board is already enough to operate such kind of devices, so that when we think about the output bias of the solar cells, which is around like 0.7 or 0.8 volt, but it can be quite compatible. So the other option is that to operate such kind of organic electrochemical transistors, and also the other point is that the current matching is also really important. So for the current matching, the size of the active area is also important. So by combining those designs, and we could simply think that the devices can be integrated, but how we can be integrated, it is also the other point. But the OECT can be applied into the ECG sensors or EOG sensors and EMG sensors. And as already Shiming said, those skin compatible designs can be attached on the skin surfaces, and we could get the very good signals using the under the motional movement of fingers, or when we grab some biases, and also when we move the eyeballs, we could simply get the biological data. This is the way how we could integrate the devices. So under the supporting glass substrate, so we deposited the pylon layer on top, and then firstly we fabricated the solar cell first, and then after masking on top of the solar cells, we could fabricate the organic electrochemical transistors between the source and drain gold electrode. So the right side, you can see the finalized cell devices. And the most important point is that by integrating those devices together, we could extremely minimize the noise signals when we measure those signals as a function of the time, so that finally we could the integrated devices attach it on the skin surfaces. We could easily get the electrocardiogram sensors, and on the red surfaces, which is under the aqueous condition, we could easily get the ECG signals on the red heart. So we successfully demonstrate the integrated system and published the paper in 2018. And thank you for the Shiming such a great cartoon in the Nature. And after that, I start my work for some serious work of regarding to the ultra flexible cables. And one is that by changing the transparent electrode to the ultra thin AG metal layer, which is only 8 nanometer thick, we could achieve the world first semi-transparent and ultra flexible cables that can be attached on the building application or on the skin surfaces for the see-through devices. And I'd like to briefly introduce the latest my work, which is tracking the finger motion via organic proximity sensors. So as you can see, when devices flip over onto the skin surfaces, we can track the positions of the devices from the specific light positions. So this is the simple idea is that, so when the x-axis, y-axis is there is the different light is located along the x and y axis, and we draw number 3, we can get the different axis data. For example, when we move the motion like this, and we can get the y-axis data in red or x-axis data in the green. And when we combine those data in the XY positions, we could draw all the numbers by drawing the finger motions and without any pens or just tracking their positions under the light. And after that, what we need to do by writing the numbers, the point is that we could build the neuromorphic devices also like a ultra flexible substrate. And the neuromorphic devices can be well operated on the replica skin surfaces. And those well function of the synaptic plasticity on the skin surfaces shows the neural network analysis of what we have drawn. So when you draw those points, then we can make the canvas like this. And then each point of the pixels goes to the input neurons. And by the neural network, we can see the output neurons and what number it is. Actually, we don't know what the canvas look like, but the computer knows how it look like. So that I would like to insist that the neural network is very powerful for recognize what we have done. And we also check the different persons and how the computer will recognize what they drawn. And finally, we could achieve the 85% and up to the 93% of the accuracy was achieved by applying those data, memorized data in the neuromorphic devices. And we could successfully show the first proof of concept on the sensor and neuromorphic and AI integrated system, and which was published successfully in Nature Electronics in 2023, last year. So this is my oral talk. So finally, I would like to say thanks to all the collaborator and all my students and the research funding. Thanks very much for your attending. Thank you.
Thank you very much, Professor Park, for your wonderful talk. Very impressive research output. So let me welcome Professor Jia Liu from Harvard University. So before his presentation, let me introduce Professor Liu first. So Professor Liu received his PhD in chemistry from Harvard University in 2014, after which he completed postdoc research at Stanford University from 2015 to 2018. He joined the faculty of Harvard School of Engineering and Applied Sciences as an assistant professor in 2019 at Harvard University. Professor Liu's lab focuses on the development of soft bioelectronics, cyber engineering, genomic engineering, and computational tools for addressing questions in brain-machine interfaces, neuroscience, cardiac diseases, and the developmental disorders. So Professor Liu has pioneered in bioelectronics, where he developed new paradigms for soft electronic materials and nanoelectronics architectures for tissue-like electronics, as well as their application for long-term stable brain-machine interface, high-density cardiac mapping, stem cell maturation, and multimodal spatial biology. His work has been recognized as a milestone in bioelectronics by Science in 2013 and 2017, and as the most notable chemistry research and top 10 world-changing ideas in top 15. He has received numerous awards in his independent career, including the 2022 Inventors Under 35 Global List by MIT Technology Reviews, the 2022 Young Investigator Program Award from the Air Force Office of Scientific Research, and the 2021 NIH NIDDK Catalyst Award from the NIH Directors Pioneer Award Program, and the 2020 William F. Milton Award, and the 2019 Aramont Award for the Emerging Science and Research Fellowship. He is also the co-founder and scientific advisor of a brain-machine interface company named Ajou Inc. So, Professor Liu, please, the floor is yours.
Thank you very much for your introduction, and thank you for inviting me here. So let me share the screen. Is that okay?
Yes.
Okay. So I will, should I wait for the changing? Okay, should be good evening, everyone. My name is Jia Liu. I'm an assistant professor at the School of Engineering and Applied Science at Harvard University. And today, my talk is about the soft and flexible bioelectronics for the brain-machine interface. So in the very beginning, I want to have the disclosure of my conflict interest and acknowledgement. So I'm a co-founder of the Xsoft, which is a brain-computer interface company. And we are also involved in the human clinical study, which has been approved for the human device implantation. And the work that I'm going to present is done by my lab members and fantastic collaborators at Harvard and MIT. and in many other university. And we also receive the fundings from the following funding agencies to support our research. So my lab's research interest is mainly about, for example, how those kind of neurons in the brain like function together to give rise to certain behavior, all the malfunction of the cells that give rise to the disease, and how those like a different type of the cell that is assembled together into a full functional brain to conduct like a behavior. To specifically, like we are very interested in converting the high performance nanoelectronics into the flexible and soft bioelectronics for the long-term stable brain interface to address those questions, and further integrate those technology together with the state-of-the-art spatial biology technology to look at the tissue modality from the different angles to address those questions. So before I introduce the technology that we are developing, first we want to discuss what's the challenging in this field that we try to address. So to build like the effective like a brain-computer interface, the first one that we need to address is really the single cell activity across the entire 3D brain really matters. So on the left, that is the functional MRI imaging of a human patients. And on the right, that is the calcium imaging of a zebrafish brain, and which is a transparent species. And on those like two images, those red color label where the neuron that is really firing. And you can see that from the functional MRI imaging, that is the human brain really need to recruit the neural activity that is fully distributed across the 3D brain to collectively define the patient's brain internal state. And on the right is like those functional MRI, functional calcium imaging really show that those fish also needed to recruit the neuron distributed across its 3D brain structure to define its behavior state. So if we want to collect those like activity at a single cell resolution across the entire 3D volume of the brain, then we immediately will face the second challenges in the neural engineering. That is the spatial temporal dilemma. Because those each individual neural activities operate at the millisecond time scale, this action potential, and it will confine into the individual neurons at the spatial scale from like a 10 to 100 micrometer. But we know that the brain does not operate at a millisecond time scale, right? It takes days, months, of years to build up the cognition, memory, emotions, and recruit like millions to billions of the neurons, distributed across the 3D volume of the brain at the spatial scale from centimeter to meters. And given there are huge number of the neurons of different species, that the bandwidth that we need to provide to collect their activity requires like a bandwidth at the hundreds of gigabytes to thousands of terabytes per second. And then there's a third like a challenging, that is in the brain, like different neurons will have the different gene expression. They will have the different like morphology and connectivity, and together they will give rise to the different kind of electrical activities. So this kind of the cell type specific information also need to be integrated together with their electrical recording and control to decode the brain activity. But why we think, even given those like a lot of challenges, why we think right now we have this unique opportunity to address this problem? Because on one hand, driven by the Moore's law, the number of the transistor on each individual chip already goes to the number that is equally to or even higher than the number of the neurons in the human brain. And on the other side, the nanotechnology has already miniaturized the sensors and the detectors and the stimulators down to the subcellular size. And in the in vitro setting, that we already can long-term stably like address the single cell activity in a long-term stable manner. So you can say that on one side, that is our like a human brain with billions of neurons. And on the other side is our powerful computer chip with billions of the transistor. What we are missing right now is really a cable, a scalable interfacing technology that can bridge the electrochemical impulses in those like neurons in our human brain to our powerful hardware to decode their activity. So what does this like scalable interfacing technology that require? I summarized it here. So the X and Y, that is the time and the spatial scale. And this two dash line is the resolution, the single cell, single spike spatial temporal resolution, the technology that need to achieve. And then there's this third dimension that is the cell type specificity that need to be incorporated. And for the traditional bioelectronics, they can easily achieve the single cell, single spike spatial temporal resolution. There's no problem. However, you can say that their performance cannot last for a long time in the biological system. They cannot be easily distributed across the 3D tissue of the brain without the damage to the brain structure. It cannot integrate the cell type specificity. So since we already have such like a powerful semiconductor fabrication technology, why not we just use those technologies to build the powerful bioelectronics to look at a large number of the neurons activity at once? So actually, people already done so. So this is the neural pixel technology that is fully leveraged the semiconductor fabrication technology using the CMOS driving multiplexing circuits, integrate thousands to 10,000s of the microelectrode onto one brain probe. So that implant that into the brain, you can look at thousands of the neural activity at the same time. However, they don't have this like a long-term stability at all. So over like a couple of days or months, like the signal will completely disappear from those kind of rigid probes that are implanted into the brain. So in the first part of my talk, I want to introduce you how we build the tissue-like nanoelectronics to provide the long-term stable interface at the single cell level to capture their electrical property. But before that, we need to first understand what is the fundamental limitations, what's the challenge to prevent us to capture this long-term stable neural activity. So turns out it's really coming from the size and mechanical mismatch between the biological brain and the electronics. So biological brain is extremely soft, like a tofu, but electronics is very rigid. So put like a blade. So put the electronics into the brain, and when the brain is moving, those electronics will cut the brain at a micrometer scale, causing the drift of the sensors inside the brain, so that you cannot stably capture activity from the same neuron. And in addition to will trigger the huge immune response, the foreign body effect from the brain to those like a rigid like a probe, so that over the time you will have a degradation of the neurons and the proliferation of the immune cells at the interface between the brain probe and the neural tissue, so that you will lose those single unit action potential that you can record in the very beginning. For the patients with deep brain stimulator implanted every couple of months of a year, you need to relocate the stimulator position to find a healthy neuron to do the stimulation. So like when we look at this question almost like a decades ago, we asked ourselves, like if we look at the history of the mankind, like made the device or material, is there any kind of material that can bypass this size and mechanical mismatch with the biological system, provide the long-term stable interface with the biology system? So actually there is this kind of a synthetic tissue scaffold, which is a 3D micropores, soft, like biopolymers that can allow the cell to grow into their matrix, and after that you can transplant them back into the human body without the trigger this kind of long-term chronic immune response to those implants. And we are thinking that why not we build the electrons to fully mimic their structure. So the electrons also have the 3D micropores structure, subcellular feature size, and tissue level mechanical property. But most important that to make the technology scalable, the electronics that we build need to be fully compatible with the state-of-the-art lithographic fabrication, so that any like hundreds of tens to the hundreds of the sensors that we build in the lab can easily translate into the semiconductor foundry to make like thousands to millions of them. But the problem is that at that moment, for all the material that is developed for the semiconductor fabrication, for the lithographic fabrication, they have the Young's modulus at least 6 orders magnitude higher than that of the biological tissues. Indeed, there's some of those soft material which have the Young's modulus that are compatible with the biological system, but they are not compatible with lithographic fabrication at all. So in the very beginning, we cannot even make the tissue level soft electronics. We can only make the tissue level flexible electronics, because the flexibility of the device is not just related to its Young's modulus, but also related to its thickness. Then we can still use those rigid material that is compatible with lithographic fabrications, but make them into a very thin structure so that to bring those rigid devices into the tissue level flexible regime as a tissue level flexible electronics. So this is like in 2015 that we published a paper that we designed this tissue-like mesh nanoelectronics. That is a 2-layer of the SU8 sandwiches the 1 layer of the metal as this mesh structure. The total thickness is less than 1 micrometer. So you can see how flexible those devices are, that they can easily syringe inject into the brain through like a syringe needles. And of course, like recently, we further improved this implantation process, like that can safely implant those mesh electronics across multiple brain regions. And the green color that is labeled the neuron, purple color labels the astrocytes, and those red color label the mesh electronics that are implanted into the brain. You can see that after months of the implantation, the mesh electronics completely merge together with the neural network that without triggering the significant degradation of the neurons and also the proliferation of the immune cells. And when we look at the signal that we can capture from those mesh electronics implanted into the brain, we found that those like waveform is remarkable similar, like over this kind of more than like 1 year of the implantation, that we can almost say that we can capture the activity, not just like stably from the neuron, but almost stably from the same neurons. So to verify it's like a stability, that we can design this high density flexible mesh like nanoelectronics with this high density sensor array so that one neuron activity can simultaneously captured by the multiple electrode on those mesh electronics. You can see that over this like a month-long implantation and recording, it's not just the waveform that we can capture from those each neurons that is stable, but also the distribution of those waveform across the multiple sensors are also stable. Like fully like suggests that we can long-term stably capture the activity from the same neurons by using those flexible electronics. So that this part that we developed this tissue-like electronics that we can enable this long-term stable interface with each individual neurons in the biological brain, which allows us to substantially extend the time like coverage on this kind of brain-computer interface. And since we published the paper in 2015, we can see this like wave of this kind of adoption of the technology, not just in academia, but also in the industry, that so many like a startup company adopt this like a flexible electronics design that for the long-term stable interface with the biological system. However, then the second question is still here. That is, even we can enable this long-term stable interface with the brain, how we distributed them across the 3D of the brain, how we scale up the number of the sensors that we implant into the brain without substantially damage the brain. So currently, like the state-of-the-art solution in the industry is that we implant so many of the electrodes. The problem is that because you still use a very rigid material, but just make them into a very thin structure to enable the tissue level flexibility, so that for each brain probe, there's a very limited number of the sensors that you can fully integrate it. For example, in those Neuralink technology, every brain probe, they can only integrate 8 to like 16 electrodes, so that when you want to implant over thousands of the electrodes into the brain, that you need to implant over like 100 brain probe across the 3D brain tissue. Basically draw those like hundreds of holes on your brain. That's why they need to have this kind of automatic like implantation machine for the implantation. But to reduce the damage, the really solution is that we need to scale up the number of the electrode per brain probe. Make like a soft neural pixel that when you just need to implant a few brain probes that can already deliver thousands to millions of the sensors into the brain without causing severe damage. However, the problem is that since we are using the rigid material, but make them into a very thin structure to enable the tissue level flexibility. While the metal, the conductors can be made into a very thin structure, like a 20 nanometers, still maintain the enough conductivity for the signal collection. Those dielectric material, the encapsulation material, cannot be further reduced because they need to maintain certain thickness to encapsulate the interconnects and the electrode to prevent the leakage current and crosstalk between different channels. As a result, when you scale up the number of the sensors, that you will also scale up the volume of the dielectric material that you implement into the brain probe, so that the brain probe will become thicker again and become rigid, and all those problems like related to the probe drift and the immune response will come back. The really solution is not just reduce the thickness of the device, but also reduce the intrinsic Young's modulus of the material, especially the dielectric material that he used for this flexible brain probe. Now we really need to introduce those kind of tissue level soft material for the nanofabrication. But then the question is about why the tissue level, those soft material elastomers, they cannot be used for the nanofabrication. They cannot be used for the long-term stable brain-computer interface. It come out, these problems are twofold. The first one is that why the material is soft. Like academic, speaking, it is the glass transition temperature is lower than the room temperature. So you can consider them as cross-linked liquid at room temperature, or they have this microporous structure at room temperature. Therefore, they are easily swelled by the water or organic solvent that is used for the nanofabrication. And in a standard nanofabrication process, this is a layer-by-layer fabrication, and each layer will involve a lot of different developer removers that is organic solvent that easily swell those kind of dielectric elastomers that if they are need to be used in the nanofabrication. So in the first part, we need to find a solvent-resistant, chemically orthogonal, and photopatternable elastomer. And then the second problem that we found is that the ions in the solution can also easily penetrate those dielectric elastomers. Because they are cross-linked liquid, at room temperature, and our biofluids is like a 37-degree warm and salty water. So the ion easily penetrate into the elastomer that over the time, they will lose the capability to encapsulate the electronics because they become the ion conductor. But we also need to have this long-lived elastomer in the physiological condition. So if you consider that ultimately we need to have an elastomer which can strongly repel both like a water, organic solvent, and the ions. From the chemistry perspective, there's only one type of the elastomer that can fulfill those tasks. That is the perfluorinated elastomer. So that we develop this perfluorinated elastomer and make them as a photoresist. And we compared it with the standard dielectric plastics like SU8 that are already being used in the long-term stable brain-computer interface. You can say that in the biofluidics, their performance is as stable as the SU8. And meanwhile, they can be made into the very soft structure, as soft as the brain tissue. And they are strongly repel all those kind of organic solvents that are used in the nanofabrication so that we can do multi-layer nanofabrication, vertically integrate the number of the sensors onto one brain probe, but still maintain the brain level mechanical property. And after implanted into the brain, you will introduce the minimal immune response and capture the activity from the same neurons over the long time. This technology is such a scalable technology. It's like potential cannot be just done if we just fabricate hundreds of the electrodes by using those technology. However, in the academic lab, it's really hard to really leverage the semiconductor fabrication to integrate like millions of the sensors onto those devices. If I ask any of my students, say like fabricate 1 million sensor in the academic like a clean room, I think no one wants to do the PhD with me. So after this technology has been developed, we incorporated a company called Xsoft, really leverage the semiconductor automatic manufacturing process that enable us to integrate like hundreds to the thousands of the electrode onto each brain probe. And we also need to design the electronics to decode the brain activity and also develop those like algorithm to decode the brain state. And after that, after 3 years of development, we have made this perfluorinated elastomer-based photoresist commercially available. And we can do this large-scale brain probe fabrication using the automatic semiconductor fabrication process, and we got the breakthrough device designation from the FDA so that we can move forward with the human clinical applications. And meanwhile, that we develop those like technology that can be used for the academic settings, that we can long-term stably capture the electrical activity from the freely behaving animals from the same neurons. We also partnership with the TMSC to integrate those kind of ASIC design for our like simultaneous recording and stimulation chips that go to the up to like 4,000 of the sensors. So this is definitely one direction that we try to scale up the number of the sensors into the brain. However, if you look at the brain architecture, for example, this is the beautiful work that done by my colleagues, Professor Jeff Leckman at Harvard. They use the EM to scan the 3D connection of those neurons in the fully matured brain. You can find that when the brains get functionally matured, even in this tiny region, this 20 times 20 times 40 micrometer region, there's over like hundreds of the like different cellular components that are fully interwoven together. So that when the brains get functionally matured, the neuron connected with each other at a nanometer resolution. So that no matter how soft and how flexible you design those devices, as long as you implant them into a functionally mature brain, you need to break the neural connectivity at the nanometer resolution. So this is a kind of acute damage that cannot be avoided. So how to address this? Turns out the nature already provide us the solution. So over the time course of the brain development, the 3D brain is actually coming from a two-dimensional cell sheet named the neural plate at the embryonic stage of the animals. And the neural plate will first fold into a neural tube, and with the further folding and expansion, it will grow into a 3D brain structure. So that instead of just make the tissue level flexible electronics, we make the tissue level like stretchable electronics and integrate those stretchable mesh electronics with the neural plate. And when the neural plate fold into the neural tube, they will have a chance to internalize the electronics into the 3D brain structure. And with the further growth, it will help this developmental process will help distribute the sensors across a 3D brain without damaging the neural connectivity. So we are testing this idea firstly on the stem cell derived organoids. Because the stem cell derived organoids basically mimic this kind of in vivo 3D developmental process. It starts with the 2D stem cell sheet layer, and then when they, like after days of the development, they start folding into a ball-like structure and ultimately grow into the 3D organoids. Then we can design this stretchable mesh electronics integrated with the 2D stem cell layer, and when they grow into the 3D organoids, they distribute the sensors and the electronics across the 3D volume of organoids. You can see that this is how we design this stretchable mesh electronics. Very easy. We adopt those serpentine-like structure, interconnect structure that have been well developed by Professor John Rogers at Northwestern. And we implement them into our like mesh design. And you can see how stretchable they are after they have been released from the substrate. Even the floating of the water can easily stretch them. Then we can integrate them with the 2D stem cell layers. And you can see that after 3 days of the culture, they start to fold into a ball-like structure. And after 20 days of culture, they grow into a 3D organoids with the electrons completely distributed across the 3D volume of the organoids. And we call this technology cyborg organoids technology. We can induce them to virtually any type of the organoids. For example, we can induce them into the cardiac organoids. You can see that because this seamless integration of those electronics with organoids in 3D, they can fully accommodate this kind of cardiac contraction of the organoids. We can capture the action potential stably across a 3D volume of organoids. We can even capture the gradually evolved action potential over the time course of the tissue development, start with this slow calcium-like activity, gradually emerge hyperpolarization, and ultimately generate depolarization. We can induce them into the human brain organoids, those like the mini brain, the petri dish, with the electronics fully embedded, and capture when the action potential first is generated from those kind of brain organoids development. We can integrate them with the real living animals embryo. You can see that this neural plate to neural tube formation process will internalize the electronics. And when this like embryo grow into the tadpole with the electronics fully distributed within their brain, that we can capture this gradually evolved like electrical activity from the same embryo, the same idea that is with the initial with this global synchronized flow activity gradually decoupled into this like a brain region specific faster spikes and ultimately generate those kind of a cell specific action potential from those brain regions. We can fully capture how this brain activity evolved over the time course of the brain development. You can see that we fully integrate this tissue level soft electronics together with the cyber engineering technology to allow us to distribute the electronics across the 3D volume of the brain. So the last one is that how we integrate the cell type specificity. So over the course of my career, that we try so many different type of methods. Like we integrate the micro LED with mesh electronics so that we can do the in vivo optogenetic stimulation and recording to identify which type of the neuron we are recording. Or we can genetic engineering the neurons to allow the specific group of neurons to grow a conducting polymer as the electrode to interface with the implanted electrode to enable the cell type specific recording. But in the end, like recently, that what we are really excited is to integrate the imaging-based in situ single cell RNA sequencing, also named spatial transcriptomics, with the flexible electronics to fulfill this task. So this spatial transcriptomics is functioning like simply in this way that after you have a tissue that has been measured, you can make the tissue transparent by cross-link them into a hydrogel network and remove the phospholipid bilayer. And then you can introduce those different kind of DNA probe hybridize with mRNA like in situ. And then you do the multiple round of imaging-based sequencing to read out the DNA identity and infer the RNA identity and the location. And then you go through a multiple round of the imaging, computational imaging process to assign the different mRNA to the different cell, got the cell like a mRNA copy number per cells, and go through the standard bioinformatics process. You can generate a piece of the biological tissue mapping with all the cell type like indicated. And through this method, we're not just look at a few genes or like 4 channels of the antibodies. We are looking at like hundreds to thousands of genes at the same time. It gives us the most accurate, the cell type specific information with our like electrical recording and control. But then the big question is that how we link those gene expression information together with our electrical recording, right? So the problem is that after this kind of recording, that we can capture this kind of mesh, those like soft electronics embedded with the tissue. Because the device is even softer than the cell, they can be considered as the hybrid tissue architecture and go through this kind of tissue clearing and in situ sequencing process without cause this like a dislocation between the sensors and the cell. But the big issue is that how we link the cell gene expression with their like a sensor identity. The solution is that we engineer an electronic fluorescence barcode is a piece of the polymer with this kind of structure that is patterned by the lithographic process. I will show it later. That give us the capability which the identity can be identified through the multiple round of the imaging-based sequencing. So that we can look at this like a gene expression from the cells that directly contact with the sensors and integrate their gene expression information with their like electrical recording. And ultimately, we can integrate those like information in the high dimensional space and do the multimodality data analysis. And this is the structure. You can see the sensor and the electronic barcode, a piece of the isolated polymer with the binary code, which can be fluorescently addressed. And this is a multiple round of the image-based sequencing identifies a single mRNA location in the tissue. And this, after this multiple round of the sequencing, we can integrate the cell like electrical activity with the cell gene expression and the single cell resolution. Then we can also apply it to the neural system to integrate the neural like electrical activity with their like gene expression, at least like separate the excitatory and the inhibitory neurons with like electrical performance. And how we use those multimodality data, there's so many like benefits from that. For example, over the time course of the development, the cell will, at a different development state, the cell will have a different electrical property, they will have a different gene expression. And if you just use the gene expression to define the cell development state, that the early development state, it can be easily separated from the resting development state because the gene expression is very different. But in the over this like later development period, that the cell gene expression differences are so subtle, you basically cannot separate them anymore. And if you just use electrical activity to separate those like a cell development state, they can be separated into two big clusters, but within cluster, they are not separable. But if we can integrate the cell gene expression and the electrical property together and do the cell state classification, you can see that they can well separate into the identified cluster and correspond well to their development state. And more important, this like a method allow us to look at covariance of this different modality, how the gene expression change affect the electrophysiology and vice versa. Then we can design a very simple like a machine learning model. This is sparsely reduced rank regression analysis. You can tell us those kind of electrical features correlated with the different kind of gene expression. And after we identify their correlation, we can immediately design another AI-based like a cross-modality prediction model using electrophysiology to predict the underlying gene expression or vice versa. This is remarkably important because the cell type information cannot be captured continuously. Every time if you capture the cell gene expression at this scale, you need to sacrifice the tissue and look at their gene expression. But because our like electrical recording can be continuously mapped, especially using our flexible electronics, so that we can use a continuously map electrical property to infer a continuous gene expression. And more important, like there are some like patient-specific cells, there are some like gene expression that is show the difference with this like healthy tissues. We can still use this model based on their gene expression directly predict their abnormal electrical property, which align well with this like a real recording result. And more importantly, nowadays, like we are not just looking at the multimodality data, we can even look at the neural network that has been trained by this multimodality data. For example, we can use this explainable learning that is just one step. Look at the neural network that has been trained by this modality data. It can tell us the correlation between the different gene expression markers and the electrophysiological features and the morphology features. So you can say that we build this tissue-like nanoelectronics, enable long-term stable interface with the biological system. We build those tissue-level soft electronics, cyber engineering, distributed electronics across 3D. We also integrated the spatial transcriptomics, the in situ single-cell RNA sequencing, together with our flexible electronics as in situ electrical sequencing, and to enable the cell type specific recording and the simulation. And ultimately, we use those AI algorithms to connect everything together. So what we can do, I will, because of the time limitation, I will just very briefly introduce what we are doing by using those technologies that already merge the electronics with biology across all the scale. The first one is that we are completely revolutionize the entire brain-computer interface. For the traditional brain-computer interface, the big limitations is the signal instability at the front end. Basically, every day you record activity from the completely different set of the neuron. So that in this field, the central like efforts has been focused on build the computational-based, manifold-based stabilizer. The idea is that even you record the activity from the different neurons at the different time, but for certain brain regions, such as motor cortex, the output is always a low-dimensional plane in the high-dimensional neural space. That you can always use this stable output to realign those neural dynamics. But for our technology, we don't have this problem because we can keep capture the activity from the same neuron. Therefore, those like a neural trajectory or neural manifold is also stable. Instead, we can use this stably recording neural activity as training data to directly train a neural network, artificial neural network, as animal-specific brain decoder. Because in the reality, there's no experiment that is 100% yield. There's always one channel that is somehow broken or one neuron is just dead. But for this kind of adaptive, like artificial neural network-based brain decoder, they can quickly readjust them and give like a stable output. And then we can go beyond this current motor cortex-based brain decoder. Because previously, the neural brain is a dynamic system. For most brain regions, the neural activity constantly change because the neural representation drift. Even the animal like conduct the same task or watch the same like movie over time and time, those like brain dynamics constantly change. But if your recording is also change and the brain is also change, basically you cannot deconvolute this like a change the dynamics to give a stable brain decoding. But for us, like we don't have this problem because we can capture the activity from the same neurons. And if indeed, if you look at the single cell activity over the time, this is based on the visual stimulation of the animals. This single cell level brain dynamics constantly changed. And the statistical result even show that it never stopped. But if we look at the population dynamics, use one neural activity as a one vector and look at their like reduced dimension in the latent space, we found that their like latent dynamics is go through this affine transformation. They also constantly changed, but they preserve their topology so that we can design another artificial neural network to compensate this kind of affine transformation process and use a stable recording as the input. We can give a very precise, like a stable visual information decoding. And we think that they can basically go beyond the visual cortex, can go to any kind of brain regions to build this future flexible neural AI. Because right now we can fix our like a recording constantly from the same neuron so that we are observing the brain intrinsic dynamics. And we are using the brain intrinsic dynamics not only to decode the brain dynamics, but also use that to program the future AI to enable this kind of brain-inspired artificial neural network. And finally, we'll also try to build a functional brain cell atlas. Currently, they are using the spatial transcriptomics with my collaborators that we already capture those single cell gene expression across the 3D volume of the brain. That we can use the gene expression to redefine the brain anatomy. The brain anatomy previously just like over like hundreds years is just defined by the cell morphology and connectivity. There's no like ground truth there. But right now we can use the single cell gene expression to redefine the entire brain anatomy. We can find so many like cell regions that it has not been identified before. And this is definitely like not like a single lab's efforts. There's like over like 10 labs in the world. So last year that we published like 10 like Nature papers at the same time. And then my student really built this kind of multimodal foundation model that can integrate everybody's like brain anatomies data atlas data together as a centralized atlas with over 18 millions of the cell that allow other modality also incorporated into this centralized brain atlas using the cell spatial gene expression as an anchor. So that for the future, since we already identified so many new brain subregions based on the cell gene expression, we want to capture their like electrical, the behavior dependent electrical property. After that, we have the tissue together with the sensors that go through this in situ electro sequencing and integrate the cell gene expression together with their electrical activity and behavior information into our centralized atlas, so that we hopefully can fully finish this Google map of the brain that guide us for the future brain-computer interface. Thank you.
Okay, thank you, Professor Liu, for the talk and the very impressive, exciting research. So, we share the screen. So this concludes the presentations for this evening, and I would like now to invite our panelist, Professor Shiming Zhang, to join me for the Q&A session. So before the Q&A session, let me introduce Professor Zhang first. So Professor Zhang is from Tsinghua University. graduated from the University of Science and Technology of China in 2011 with bachelor's degree in chemistry and obtained her PhD in chemistry from the Chinese University of Hong Kong in 2015. From 2016 to 2019, he worked as a postdoc fellow at the Center of Emerging Metal Science at Riken in Japan and the Department of Physics at Humboldt University in Germany, honored with the Humboldt Research Fellowship. In September 2019, he joined Tsinghua Berkeley's Shenzhen Institute and the Shenzhen International Graduate School at Tsinghua University as an assistant professor, leading the flexible materials and electronic devices research team, and got promoted in 2022. Her research on organic and flexible electronics has been published in prestigious journals, including Nature Energy, Nature Communication, PNAS, and etc., with over 3,000 citations and an NH index of 28. She serves as the early career editorial advisory board of Applied Physics Reviews, editorial board of Wearable Electronics, and as a reviewer for journals including Nature Electronics, Advanced Materials, etc. So as one of the session chairs, she organized the symposium SB02 at the 2022 MRS Spring Meeting and the International Forum on Graphene and Shenzhen in Shenzhen from 2021 to 2024. And she has received awards and honors, including Outstanding Graduate of USTC, Hong Kong PhD Fellowship Scheme, Humboldt Research Fellowship for postdoc researchers, and overseas high caliber personnel in Shenzhen Excellent Youth, etc. And so now we will take questions. So let's welcome Professor Xu, and now we will take questions from the audience and discuss the innovative research topics further.
Yes, thank you very much, Professor Wang, for the kind introduction. And indeed, it's quite enjoyable to attend these three wonderful talks on this fascinating field of flexible bioelectronics. And I'm so excited to see how this technology is evolving and the impact it is making across various applications. I do have a couple of questions, maybe firstly to Shiming. Yeah, quite informative and insightful talk. So my first question is, could you elaborate on the mechanisms by which the tissue-like OECTs mitigate the effects of noise and perhaps a signal interference in complicated wearable scenarios?
Okay, so thank you for the question. I think I need to go to the slides here. Yeah. We can show the slides, give the slides here.
Yes.
Yeah, so I think this is also elaborated, later by Professor Sanjun Park. So actually, how OECD can really increase the signal-to-noise ratio, especially in complicated wearable scenarios. So actually, also kindly introduced by Professor Liu Jia just now. Actually, we need to have the sensor to improve the signal quality, to stabilize the data at the source of the data. So traditionally, we have the sensor deployed at the backend, which means actually you can sense both the signals and the noise, for example, from the brain in this case. But you also have the noise on the line. So when you calculate finally, actually you got the SNR ratio. But if you can move the amplifier closer to the source of the data of the signal, so you will get a higher SNR because you don't amplify the signals on the line. But this is challenging for traditional, for example, silicon ones, because as also Professor Liu Jia just mentioned, so you need some material science solutions to enable that your device technology can be moved into the brain and without causing so many, for example, the antibody foreign body reaction or this kind of tissue incompatibility, right? But OECT by itself, it is an organic devices technology. It can be really fabricated by, for example, as I mentioned, use polymers or even hydrogels, right? So this part exposed to human tissues have better tissue compatibility. So in this case, you can put the sensors here, and you can amplify at the original, place or the source of the signal. In this case, by this definition, you improve the SM. This is experimentally verified in this paper by Professor George Mallers and also, in Professor Park's paper, right? So in the 2018, also, in the when he was in Professor Somaya's group. I think this is the reason.
Yeah, thank you. And you have also mentioned the OECT that integrates hydrogel functioning as the active material, right? So how to make sure that the structure that is infiltrated with water still maintain effective pi stacking for effective electron transport?
Good point. So I didn't put so many data here. So if you're interested, you can go to this paper. I think it's published 4 years ago. So actually, we first of all, it's called a multi-network hydrogels. So here we have the conducting polymer P.PSS, which is actually the active material of the most OCT, right? So use P.PSS semiconducting polymer. But what we can do actually, we can first actually form a P.PSS hydrogel layer. Okay, but in that case, we need to do some topological control, right? To make sure that ions can penetrate in and out. That means we need to do, for example, in this case, we may sometimes do the freeze drying or salt it out to make some micro holes. But then we can actually further penetrate another stretchable network. Maybe you know that, for example, polyacrylamide or even other kind of stretchable network to form an interpenetrated network. Sometimes you also may want to use, for example, the sodium calcinate, right? These kind of networks. But in our case, I think we have the triple network. But the most important part is conducting polymer network, right? And all the parts are just to contribute the stretchability or contribute to the micropores in that film. And you can see here, actually, we also cannot make them too thick. For example, here we make them fiber-like, but the diameter is around, let's say 10 to 100 micrometers in diameters, or we found that it functions well, right? But actually, we are furthering research in these directions to study quantitatively, right? How the ions, electrons, and etc. interact with in such a conducting polymer or semiconducting hydrogel system. But definitely, there's a lot of things to do.
Okay, thank you so much. And maybe a very quick question regarding the printing technique that you have also introduced, which is quite interesting. Since you and both Professor Liu Jia have mentioned about the special temperature resolution, which is always a request for the integrated systems, right? So you have achieved 100 micrometer resolution. So in order to further decrease the footprint of the devices, what are the current limits? And is it possible to integrate both P and N-type channels so that we can make integrated circuits using the printing technique?
Yeah, it's a good question. Yeah. So actually, we are a bit conservative here because there are some advanced printing technologies that you can claim, for example, even down to 10 micrometers, for example, aerosol gel printing or many others. But because we actually focus on one-shot printing of multi-channels, that means, it really depends a lot on the material ink. For example, you may know that if you want to print the P.PSS, actually the single molecules or the polymers, the diameter is hundreds of nanos, right? So, and also there's clogging issues. Sometimes you need to do a filtering. So this really create a lot of trouble. So to have this resolution, actually this is threshold resolution for all these materials. Okay, that means for example, P.PSS can be achieved. We can claim some, for example, silver can be much lower resolution, or lower means the value is lower, for example 10, but it doesn't meet all the requirements for all the materials. I think specifically if you target a simple metal lines or let's say less material combinations of the electrodes, you can target high resolutions. But if you really target a fully functional transistor or because this is multi-layer, right? You have the canonic polymer, canonic hydrogels, insulators, electrolytes, etc. So in this case, you may have to make a balance. In this case, I think this is so far the best we can achieve. But of course, there's many things we need to do. 100 micrometers, I think, is okay for our on-skin applications, but definitely for the electrodes, I think we need to further think the size. Right? But this, currently, I think flexible OECTs are there, but we need to have some advanced, let's say, material inks, right? That can be able to print it, to lower the resolutions.
Thank you for the insights.
Thank you.
And Songjun, congratulations to your achievements as well. And thank you for the wonderful overview from OPVs to OPV and OECT integrated systems, and then the OPDs for motion capture. So my question is how to connect the front-end optical sensor with the back-end data processing unit in your OPD systems for the motion capture? Andrew, maybe you have muted yourself.
Oh, sorry. Thank you very much for your comment. So first of all, our devices was initially fabricated individually, and then we checked the possibility that we can use those devices as a proximity sensors and the neuromorphic devices on the flexible substrate first, and then after we measured the 2D canvas data from the organic proximity sensors, we put all the data into the neuromorphic array. But basically, as you mentioned, we didn't connected the devices physically, but the data of the recorded 2D canvas data added onto the neuromorphic arrays. And then we did the artificial neural network systems to recognize what we have done. So we actually didn't the fully integrated system, but we give a concept of the integrated system itself. So this is the comment I can give you.
Thank you. And looking forward into future applications, maybe like how might such advancements in flexible optoelectronics could transform our daily life in perhaps sectors like healthcare, medical diagnostics, or virtual reality? And what would be the next big milestone that your team is aiming to achieve now?
It's a really good question, and I'd say that there is no limits. I mean, first of all, by using the light, I mean, for the organic photodiode, we are trying to use them as a different type of application. For example, the devices can be response under the near IR light, which is the people cannot see those visible light at all. That kind of condition, we can operate them using the biomedical monitoring or 24 hours monitoring system for biological data. And also, as I shown before, I mean, those proximity sensors is one of the other options to check the finger motion, not only the finger motion, but also the gesture, the motions that can be attached onto the skin or textile surfaces that can be applied into the AR or VR or mixed reality life, and then those data can be applied into the human motions, and those all the data can be recorded at once, and then we can recognize what the people used, and their motion can be applied into the game or baseball or maybe operation of some kind of machines. So I could think that those applications can be the recent aim our team. So we are trying to develop the high quality of the optoelectronic devices for the attachment into the skin or the textile surfaces.
Yeah, thank you. Look forward to the future advancements. Yeah.
Thank you.
So if I still have time, maybe I do have a couple of questions for Professor Liu as well. Quite passionate and beautiful talk. Thank you so much. So you have mentioned that you could actually capture the activity from the same neuron using the mesh-like structure. So how did you prevent the shear motion? Because as you also mentioned that the brain always moves around. So did you apply any interfacial adhesive materials?
No. So the key is to design this into this mesh structure, right? So once you implant those mesh structure into the brain, over the time, the neuron will grow across those mesh network and form like an interwoven structure. So for those devices, it's like easy to be implemented into the research, into the animal work. Actually, it cannot be directly applied for the clinical, because for the clinical application, every implantable device need to be safely retrieved from the brain tissue. And if the tissue completely grow together with the device, when you retrieve that, either the device will break inside the brain, or it will damage, it will drive like a large amount of tissue together outside the brain. For the research, it's very nice because after that, the cells like fully interwoven together with the mesh network and provide the best like a stabilized signal. But for our like a human clinical like a trial, that we also design those kind of ultra soft electronics, and we test it on the animals, and it seems can provide the same level of the stability. And for those devices, they are even softer than the tissue, that after the implantation, the tissue can heal and completely like sandwich the device in the middle. And they are, so that they need to become stretchable with enough like a stretchability, the toughness, so that they can be safely retrieved from the brain.
Yeah, thank you. That's very inspiring. And another question, you have mentioned about the 4,096 channels, which is amazing, right? So how about the energy management of such? Yeah. And did you incorporate some sustainable energy sources or energy efficient technologies? Yeah.
That's a very good question. So currently we are still designing it as a wired system. So we and for our like human version of the device, we plan to implement the battery, but that is still like under the development. We are currently version that we are still using the wired connection to power the device.
Yeah, thank you. And if I understand correctly, this system also is based on the passive electrodes, right? So
Yes.
You are still using metal as a
Yes.
sensor. Yeah. So maybe Shiming and I could be wondering the same issue that for metal you have the planar capacitance, right? So if you decrease the size of each sensing spot, then perhaps it's more challenging to sense the low amplitude signal. So how to solve this issue?
We don't solve this issue because there's no such need that you need to further reduce the size of the electrode. Because after all, the neuron is pretty large compared to the nano device that we can fabricate. Neurons have the size from like depends on what type of neuron, like a 10 to 50 micrometer. So that for the PT electrode with the 15 micrometer, it can safely record the single neuron action potential long-term stably from the tissue. And also we, like as I showed that we design this, this is very important that you need to design this high density electrical array. So that ultimately this kind of signal that you record from those cells captures help you to identify the single cell activity is from the spec sorting based on the distribution of the waveform across multiple channels that give you the highest stability. And in fact, that we tried so many different type of material regarding their stability. For example, we coat the electrode with the PSS, but over the time it disintegrated in the biological system. you change the impedance. And since we need to use this stable waveform to identify the neural activity, those like if the interfacial impedance constantly change, then that will strongly interfere the ability of the device to identify the activity from the same neuron. Then we even test the PT black, and surprisingly, that the PT black in our system, maybe like we are not making it in the best like correct way, but we found that it can provide a stable recording for a couple of months. But when we talk about year-long recording, we found that like a PT itself is almost the only material that we identify that can provide this kind of a long-term stable recording.
Yeah, that's actually great news because we are always wondering what's the upper limit, right?
Yeah.
Yeah, thank you so much. Okay, so maybe time is limited. If I could have the last chance to ask all the speakers, like, what would be the most promising translational applications for flexible bioelectronics in the very near future? And what are the major regulatory or technical or ethical obstacles that must be overcome for us to move from research to the real world applications?
Can I give a comment first?
Of course.
Sure. So I'm thinking that I'm doing some of the organic materials for the device fabrication and also oxide material electronics. My concern is that the durability of the material itself. So when we use them as a application on the skin or tissue surfaces, sometimes the devices can be degraded under the mechanical deformation. And that is the reason because of the material durability itself or because of device architecture. So I think the two of things are quite important issues for the further development of the realization of the device application in the future. So I think the new materials or the durable designs are quite important for the future.
Thank you.
Yeah, maybe I can supplement a few words. So I think it's really application specific. So some of them maybe you need some temporary use, for example, disposable, or
Right.
so this kind of trends in the electronics also very important. But I think that's for translation, in my opinion, just in my narrow field, right? My understand this can be two directions. One is why not go, I work a little bit on CGM. So CGM is already successfully deployed in the market, right? It's not in the market growing very fast. I think there need to be some other biochemical sensors in addition to glucose, which is high concentration, right? So we need to develop some others can be relevant to other diseases, for example, cancer, or even insulin, other kind of biomarkers. So this we need better sensors to just go into the line with the CGM. Another one I think is definitely the trend is Professor Luja is doing the brain-machine interface, or even others, for example, spinal cord, right? So there we need some advanced electrode technologies to really solve this kind of clinical issues. And then there are a lot of things to do that can have some huge translational issues. So there you can either have short-term use or long-term use, right? So it depends really on which kind of scenarios you want to deploy your sensors. Yeah.
Thank you for the insight.
Yeah. But for me, because I'm working on this flexible electronics for the brain-computer interface, right? And I'm working both like in academia and also we have a startup like try to push it to the clinical application. Right now, we say this is definitely like the most exciting direction, that is a flexible brain-computer interface. As I just like discussed, that they can address those major limitations in the conventional brain-computer interface, provide a long-term stable interface with the brain, enable the scalability that allow us to scale up the number of neurons that we can record from the brain. And also although the translation is promising, but definitely like and the technology is fully ready nowadays. Like the challenging is the regulatory process, that we need to have a multiple step from the safety to the efficacy to the ultimately like what is the best application in this field. That is need to go through this whole FDA process. But we found that both like the US FDA and also the China FDA, previously called CFDA, I forgot the new name. That is a very all want to push this direction in an accelerated mode to enable the human clinical application as soon as possible. And moreover, it's not just like a brain-computer interface. I think it represents this kind of a new bioelectronic therapeutics that could be targeted not just a brain, but almost across any part of our bodies, and any part that is connected with the neurons through the neuromodulation that can be used for the therapeutic effect. That is actually, from my perspective, is a next generation pharma. Moreover, like in my own lab, that we also work on the regenerative medicines, because those devices, as I just showed, it's not just like a flexible, they're also stretchable. They can accommodate this kind of a tissue volumetric change, especially during the development and the regeneration. And it opened up so many new opportunities in those areas that can bring those translational effects that cannot be imagined before.
Yeah, thank you so much for this great insight. And I do appreciate Yan as well for allowing me to ask so many questions.
Thank you, Xiaoming. And actually, I forgot to say that all the three professors should answer very well questions to receive a nice certificate. But you guys all answer very good questions. So now we will have a certificate ceremony. So the first one will be Shiming. Congratulations. The second one will be Ajou. Congratulations. And then the third one will go to Jia. Congratulations. And thank you very much tonight for your wonderful talk and participation. And thank you all for all the online attendance, and see you next time.
Thank you.
Thank you very much.
Thank you very much.
Thank you, Professor.